Hi, welcome to my channel. I am Aravindan. This is the 7th lesson in electric field. Okay, in this lesson, I'm mainly going to explain about electric potential. But these topics that I'm going to explain in this lesson or in this video, mostly not in the A-level syllabuses, but I think it's better to have this knowledge to understand the concept related to negative potential, positive potential in electric field. What does it meant by negative work done, or work done with negative value, or work done with positive value in electric field, and electric potential energy with negative value, positive value. So students have a lot of confusion regarding these positive quantities and negative quantities related to potential energy, potential, and work done. So I thought of doing this as a separate lesson, even though I call it as 7th lesson. The summary or the conclusion of this lesson is important, better to know that, but the mathematical parts that I'm going to use, they are not in the syllabus for A-level students. Okay, those who feel this is too much, they don't need it, you can skip this lesson and you can go to the next lesson, that is the lesson 8. Okay, 8th lesson. Okay, so first, better to think about gravitational field. That's the most well-known field. So when you drop something, gravitational field is downwards. The direction of the gravitational field is downwards. So when you drop something, you would have learned that in mechanics, even or IGCSE, the object will move down. When it moves down, actually it's pulled by the earth. If you are dropping something closer to earth, it's pulled downwards by the earth. That means gravitational force is acting downwards and the object is moving along the direction of gravitational field. So when an object moves along the direction of gravitational field, it will lose its potential energy. Potential energy will decrease. So we learned that according to the law of conservation of energy, when its potential energy decreases, its kinetic energy will increase. Okay, same way, if I throw an object vertically upwards and when it moves upward direction, the motion is upward, the velocity is upward, the gravitational force is downwards. The gravitational force is downwards means along the direction of field. So what happens there? The object will lose its kinetic energy and the gravitational potential energy will increase. Same way, if I raise an object upwards, I am doing work. The work done by me by using my internal energy, work done by me will be stored in it in the form of gravitational potential energy. So remember this idea, remember this conclusion. When an object moves freely along the direction of field, or when field does work on the object, the gravitational field, when it does work on the object will lose its potential energy, gravitational potential energy. Whenever an object moves opposite to the direction of gravitational force, the object will gain gravitational potential energy. This idea is very important to explain or to understand the work done and electrical potential energy also. Right. Okay. So first we'll think about work done. In mechanics, you learn work done. Say an object is pulled this way, applying a force F, and if it is moved through a distance x, you learn that in mechanics. Work done, you say, normally defined in IGCSE, even in A-level mechanics, we define it as work done equal force into distance moved along the direction of force. Is it? That's the way we define. But actually, that is not the definition. Actual definition of work done in the mathematical format, in the vector format, force is a vector. The distance it moves along the direction of force, we say, that is vector. So actually, the work done is a scalar quantity. Force is a vector. It's a dot product. When we multiply two different vectors, there are two different types of multiplication there. You might learn that in mechanics A level. One is called dot product, other one is called vector product or cross product. So here work done is defined in terms of dot product. So F into x dot. Okay, dot of x. That means mod of f, mod of x, cos theta. So what is cos theta? Theta is the angle between the direction of force and the direction of x, right? That is a scalar quantity. Dot product is a scalar quantity. So this is the way the work done is defined. So actually when an object moves towards left, say something like a resistive force, in a resistive medium an object moves from this point to this point, okay, the distance it moved is going to be x towards left, but I told it's experiencing resistive force, so the resistive force may be opposite to the direction of motion. So here the work done will be Fr dot x. The angle between the force and the direction, you know, this is a straight line, so the force towards right, the displacement is towards left, x, okay, force is towards right, so this angle is 180 degree. So according to the definition, mod fr times mod x into cos the angle is 180, so the work done will become negative. Okay, work done will become negative. So it will lose its kinetic energy. When the work done is negative, it's going to lose its kinetic energy. Same way, when you throw a ball in vertical direction, okay, look at here. When you throw a stone or ball in vertical direction under gravitational field, also the same concept is applicable. When you throw a ball upward direction, the velocity is upwards, the weight is acting downwards, that's a gravitational force. The gravitational field also downwards. The motion is upward direction. You see, the displacement is upwards. So here the work done on the object by the gravitational field is going to be W is equal to F dot x. Force is downwards. The displacement or the motion, the length height it moved is upward direction. So the direction is upward x. The force is downwards. So the angle between these two forces is 180 degree. So here also, if you put F into x cos 180, the work done is going to be negative quantity. That means whenever an object has negative work done, its kinetic energy will decrease. That means it's doing work against the field, so its potential energy will increase. Okay, so the gravitational potential energy will increase when the work done is negative, right? So I'm going to use these ideas in electric field also. Right, okay. So in electric field, when I do, first I want to show that's a very common question students ask. If you are moving a charged particle in electric field, the work done, does it depend on the path it takes? No, it does not depend on the path it takes. It depends only on the initial and the final points. Okay, that also I am going to prove that, right? Okay, so to prove that, it's better to use polar coordinates. That's easy to handle rather than Cartesian coordinates. We can use polar coordinates here. So in polar coordinates, imagine we can consider like this, the direction it moves. So we can consider the motion like an object is moving from A to B. An object is moving from A to B, right? So the force acting on the object, if it is F, so I can take this as the origin, the axis. This is the coordinate, I can call it as R, right? This is the coordinate R, this is the origin. So I can have perpendicular coordinates of this force along the direction of radial Fr, the component of the force, and perpendicular to that direction, I can take the component of the force as F theta. F theta is the component of this force perpendicular to the radial direction. Along the radial, the component is Fr, and the object is moved along this path A to B through a small distance, imagine delta x. So I can give these two vectors, force F and delta x, in terms of polar coordinates. I can say the F is Fr, the unit vector along the direction of R is R cap. I can call it as R cap. That's the unit vector along the direction of radial, plus F theta, the theta is the component perpendicular to R, f theta and theta cap, that also a unit vector perpendicular to the direction of fr, that is the force. Same way the distance, I can call distance, the distance it moved along the path, a small distance dx, I can give dx as same way r dot dr plus theta cap, that is theta cap is the unit vector, into d theta. Okay, d theta is the angle in polar coordinates r theta. So the work done is given by W equal f dot dx. So when I multiply these, r cap fr plus theta cap f theta dot, then r cap dr plus theta cap d theta. But if you consider r cap into theta cap will be 0, because you know they are perpendicular to each other. They are the right angle unit vectors. So when I solve it, it will become r cap into r cap unit vector. So fr dr mod f mod dr into angle is 0 degree, because they are parallel vectors, r cap. Same way r cap into theta cap, they are 90 degrees, so cos 90 is 0, that won't be there. Theta cap into r cap, again it's 90 degrees, so there won't be any value for that, because cos 90 is 0. Then theta cap into this one, theta cap into theta cap, that is unit vector f theta d theta. Okay, so that will be the work done in two-dimensional surface, that is on a plane, in terms of polar coordinate. Okay, so I can call this dw if I want, so small work done dw. So dw is equal to fr dr plus f theta d theta. If I want to find the total work done from A to B, I should integrate it, is it? That is the summation, because work is a scalar quantity. Summation means integral of dw from A to B, right? So I should integrate it. These factors fr dr plus f theta d theta A to B. Okay, I hope you understood. That's the way actual work done is defined. Remember that. Okay, now I am going to consider. Now this one I did very just commonly. I didn't talk about electric field or anything. Just generally I wrote the work done in terms of polar coordinates, right? Now if I consider electric field, right, what will be the work done in electric field? So I'm going to use the same equation, but now consider like same thing. I'm going to use the same equations what I derived now. So consider in two-dimensional space, right, there's a charge capital Q is kept in space. I'll take the coordinates of the charge Q as the origin, so I can draw the coordinates here, and a charge particle is moved from A to B. So here they take it as this one point P. At point P, charge Q is kept. So a charge particle is moved from A to B. Consider small distance delta x or dx. It's moved from here to here. So when the charge particle at this position, a charge particle Q is moved, right? So this is the distance r of the charge Q from capital Q. And you know that I took two different component of forces. I took the force at an angle, the earlier diagram, and I told the components, the radial force along the direction of radial F R, and the component perpendicularities, I took it as F theta. Isn't the previous example? That's the way I got this equation. Now look at here. When I consider electric field, according to Coulomb's law, that is an experimental evidence, right? According to Coulomb's law, the force acting on the charge particle Q at this point, when it is at this point, is only along the radial, and F theta is equal to 0. understand, according to Coulomb's law, you know, like charges, I take this as a positive charge, this also positive charge. So the repulsive force will be along the line that connects the two positions of the charges. That is the radial field. So Fr exists, F theta will be equal to 0 for electric field. So the work done in moving a charge from A to B, the same expression, but only changes F theta will become equal to 0. So my final answer will be, this is 0, right? For radial field, according to Coulomb's law, F theta will be equal to 0. So when F theta becomes 0, the finally the answer A to B, the integral will become again integral A to B Fr dr. See, it depends only on R, the coordinates A and B. That is, the work done depends only on the coordinates, radial coordinates of the two positions A and B, not in theta. That means it does not depend on the path it takes or the angle it changes. It depends only on the R of A and B. A and B, R means whatever the path it takes to move from A to B. So if I draw the point A, this is the B. The path I drew is something like this. So if it moves from A to B along this path, or it moves from A to B in this way, or if it moves from A to B in this way, whatever the path it takes, the final work done does not depend on theta. Theta decides the path, the angle changes. It does not depend on theta. It depends only on the initial and final positions coordinates, that is the R. Okay, so that means the work done does not depend on the path we take the charge particle in electric field. Work done depends only on the initial and the final positions. So this type of field, a field in which a force field in which the force field in which the work done depends only on the initial and the final position and does not depend on the path. This type of field is called conservative field. Okay, this type of field is called conservative field. So electric field is a conservative field. Okay, I hope you understood about conservative field. Okay, now we'll get some expressions for work done in electric field. What's the meaning of potential difference when charge moves from point A to point B or point X to point Y or whatever it is. Then what does it mean by electrical potential energy? What's the meaning of negative potential energy, positive potential energy? Okay, we are going to get some idea about that in terms of mathematical equations. Okay, so we'll imagine in space there's a charge Q. It create a point charge Q kept in space. It will create electric field around it everywhere. In that field, a charge symbol Q, both are positive, is moving from A to B. So a charge Q is moving from A to B in its own. So it's going to experience an electrostatic force towards B. So that force is opposite to the direction of motion. So obviously it's going to slow down, is it? So I already explained when you throw a ball in vertical direction, it slows down. When it slows down, it will gain gravitational potential energy. So here also the same idea. It's moving in opposite to the direction of electrostatic force. So actually it's going to gain electrical potential energy. So it will slow down, right? So the angle between F and dx, dx is the distance. So during the motion from B to A, I consider a small displacement dx. Okay, small displacement dx. That dx is opposite to the direction of F. So the angle between F and dx will be 180 degree. Okay, so we know the work done is given by small work done. dW is given by dW equal F dot dx in terms of vector. So they are in opposite to each other, the direction. So that will be mod F time mod dx into cos 180 because they are in angle is 180 degrees. So cos 180. So F is equal to, we know that it's a Coulomb's law, is it? According to Coulomb's law, at this position, I can say the distance of charge particle Q from this, I can take it as x, the direction, the distance from charge Q, I'll take it as x, that is x. So the force F when it is at this position is KQQ over K capital Q symbol Q over x squared into dx cos 180, that is minus 1. So that is going to be minus KQQ over x squared, that is dw into dx, is it, into dx. Okay, so the total work done means, you know, summation. Work is a scalar quantity, so just we need to add all the work done when it moves from B to A. So summation means it's integration. So I can say the total work done is equal to integration from B to A. It's moving from B to A dw, that is minus KQQ over x squared dx from B to A. So that will be from xb to xa, that is minus, I can take the minus out, minus kq common k qq integral of x squared 1 over x squared dx, that is from b means xb to xa, xb to xa. B to a means in terms of x, the limits are xb and xa, is it? So when you solve it, you know how to integrate. It will be x to the power 1 over x squared. It will be minus 1 over x. You will get it. I will continue here. So w will be minus k q q minus 1 over x from xb to xa. So that will be, you will get answer finally, q into, you can write this q into, it will go xa, q into kq over xa minus kq over xb. Solve it, you will get this answer. Okay, now consider like this. We'll analyze in different approach. Now, if B is much far away from this charge Q, say theoretically I can say B is at a distance, at infinite distance. Yeah, there's no value for infinity, it's undefined, but we can take it's much far away from charge Q. Then that means mathematically we say xb approaches infinity, right? So when xb becomes infinity, you know 1 over infinity is equal to 0. So that time the work done will become W equal to K Q, bring it inside Q over XA, K QQ over XA. Okay, so actually what is this mean? What does it mean? This one, this is 0 because xb becomes infinity, this quantity will become 0. So work done becomes kqq over xa, means this quantity gives the amount of work done by charge q when it moves from infinite distance to point A. This is called electrical potential energy of the charge q. Careful, this is called electrical potential energy, EPE, electrical potential energy of the charge Q. Electrical potential energy of the charge Q. So how we got that? How did we get this expression? Say xb is infinity. That means the electrical potential energy. Now, one minute. If Q is not there, then there is no potential at all. If Q is 0, that will be work done will be 0. I told that in my first video. When there is no charge, there is no work required to move the second charge. If there is no charge, we can move any charge without any work on it, right? Because of this charge, it created electric field around it. In that field, this charge Q is moving from B to A. If B is at infinite distance, if it starts its motion from infinite distance to point A, the work done by the charge Q is given by this expression. This is called electrical potential energy of the charge Q when it reaches the point A. So its electrical potential energy depends on the distance of it from this charge. Careful, electrical potential energy depends on the distance of this charge from this charge. XA is the distance at A when it reaches the point A. So this is the electrical potential energy of the charge Q at A. That's very important, at A, at the point A. Okay. Okay, so here actually, at infinite distance, the electrical potential energy will be 0. When it approaches, its electrical potential energy is increasing. Now look at here. If this charge Q is negative, what will be the work done? The work done will be negative. So we should use the sign of the charge here. If symbol Q is negative, if the charge, this is a negative charge, then the electrical work done will be negative. That means its electrical potential energy will become a negative quantity. So remember that. What does it mean, negative electrical potential energy? That's a confusion students have. What do you mean by electrical potential energy has a negative quantity? What does it mean? It will be attracted by this charge. That means the charge, this one, is going to gain kinetic energy when it moves in electric field. So if it moves in electric field, if it gains kinetic energy, what happens? Its electrical potential energy will decrease. Understand? So if the charge Q moves from infinite distance to point A, and if it is a negative charge, its electrical potential energy, when it reaches the point A, it will become negative quantity. So if it becomes negative quantity, what do you mean by that? Its electrical potential energy is negative, means it's gaining kinetic energy and losing electrical potential energy. That's the meaning of it. Same way, if capital Q also negative, what will happen? The work done again is negative. If capital Q is negative and symbol Q is positive, in that situation also, this is going to move from infinite distance to point A. The total work done will become negative. Electrical potential energy will be negative. If this is negative and this is positive, what's going to happen? It's going to attract it. So negative potential energy means that is due to attractive force. So the charged particle which is moving will lose its potential energy and gain kinetic energy whenever it has negative electrical potential energy. Remember that. Okay, if both charges are negative, what will happen? Again, work done is going to be positive. Both charges are negative, that means they are going to repel each other. So that means when this charge particle is negative, this is also negative. When it moves from infinite distance to point A, it's going to experience an opposing force, and the work done will be positive quantity. That is, when it reaches the point A, its electrical potential energy will be positive. That means it's going to lose its kinetic energy and gain electrical potential energy. Okay, so remember that whenever electrical potential energy at a point is negative, that means when the charge moves from infinite distance to that point, it will lose its electrical potential energy and gain kinetic energy. Same way, when it moves from infinite distance to a point A, if it has a positive potential energy, the charged particle is losing its kinetic energy and gaining electrical potential energy. Remember that. Okay, so I hope you understood the meaning of negative potential energy and positive potential energy. Right, okay. Now, if I consider the work done per Coulomb, so that means W over Q, that is KQ over XA. That means that this right-hand side quantity depends only this charge. This is called potential of charge Q at A, that is called potential of Q at A. Okay, so kq over xa, that is work done per Coulomb, gives kq over xa, that is the potential of charge Q at point A. So if I consider this equation again, so you understood about the potential energy. Now I'm going to use this equation again, that is W over Q is equal to kq over xa minus kq over xb. That is work done in moving a charge q from B to a unit work done per Coulomb, yeah, W over q, work done per Coulomb of charge when I move 1 Coulomb charge from B to A, that is given by kq over xa minus kq over xb. That is means potential of charge charge q at A minus potential of charge q at B, that is the potential difference. So remember that when a charge is moved from, so when I continue this, W equal Q times cross multiply delta V, that is Q into delta V means VA minus VB. So remember that whenever a charge Q is moved in electric field created by another charge Q, the work done is given by the charge which is in motion times the potential difference between the 2 points, that is given by the final point minus initial point. Q into final point minus initial point. Okay, W equal Q into VA minus VB. Here also, once again, if charge Q is negative, the work done is going to be a negative quantity. What does it mean? Work done is going to be a negative quantity. What does it mean? That means the charged particle will move in the field by experiencing an attractive force. That means the particle is going to gain kinetic energy and lose potential energy. So when a charged particle moves from one point to another point, if the work done is negative quantity, that means the charged particle which is in motion will gain kinetic energy and lose its potential energy. The electric field is doing work on it. Understand? Same way, if the Q is positive, the work done will be positive quantity. That means we know that this is positive, this is also positive, means when it moves from here to here, it's going to experience opposing force. So that means the charged particle will lose its kinetic energy and gain electrical potential energy. And also we learned that potential at a point is given by kq over distance of the point from the charge, this charge, the charge we consider. Okay, so remember, finally I can conclude this video lesson like electric field is a conservative field. That means the work done of when a charge is moving in electric field does not depend on its path. It depends only on the initial and the final positions. Remember that. Second one, potential energy means whenever you have a negative potential energy at a point, that means the work done in moving a charge Q from infinite distance to a point is called or defined as the electrical potential energy of the charge. If the electrical potential energy has a negative quantity, means the charged particle is losing its potential energy when it is moving from infinite distance to that point and losing its potential energy, so it's gaining kinetic energy. Same way, if the electrical potential energy, when you calculate, it becomes positive quantity. That means when a charged particle moves from infinite distance to that point, it will gain its electrical potential energy and lose its kinetic energy. Right. Then finally, work done from one point to another point. Say W equal, if I am moving a charge from, say charge Q from X to Y, I can say the work done is equal to the charge Q is moving Q into delta V. So that is Q into delta V means final point Vy minus Vx. Remember that Vy minus Vx. We are moving from V to A, VA minus VB. Here also the work done can be either positive or negative. When you are using this equation, you must include the sign of all the charges, this charge as well as this charge, all the sign we should include. When I solve it, if I get a negative value for the work done, that means when the charge Q moves from X to Y, it will gain kinetic energy and lose potential energy. If it gets a positive value, that means when this charge moves from X to Y, it will lose its kinetic energy and gain potential energy. If it is a negative quantity, lose its potential energy and gain kinetic energy. Okay, so remember that the meaning of negative and positive values of work done and electrical potential energy. Okay, so I hope this will be useful to do the next lesson. There I'm just going to directly calculate work done in electric field, how to find the electric potential created by point charge, how to find the electric potential created by distribution of charge on a conducting sphere. Those things I'm going to consider. I feel it's better to know the conclusion of this lesson because it will be useful for the next lesson. Okay, we'll meet in during the next lesson. Bye.